We talked about the fundamental theorem of calculus sometime earlier. Today we're going to, it's kind of considered a corollary to the fundamental theorem of calculus. That means it's one of those things that just kind of grows out of it. It's almost obvious. Once we talk about it here, you're going to say, duh, that's kind of obvious. There's just one small little caveat to it that you have to be careful of, and that's what normally gets students messed up. So let's look at this problem here that I've got up here first of all. We're given a function, capital F of x, is defined to be the integral from 0 to x. So x is our variable, tan x dx. All right? So, from the fundamental theorem of calculus, what do we do with this? How do we solve just this part of the problem right here?
Integrate it, then plug in the top one on the left minus the one on the right after you've integrated and plugged them in.
Very good. Everybody with me there? All right, so we're just going to integrate, and once we find the antiderivative, we plug the top limit of integration in minus the bottom. Okay? So, what function has tan for its derivative? Have I messed up already?
No, for its derivative.
Yeah.
Oh, yeah,
Yeah, if we integrate, we've got to know what function can we take the derivative of, and it is tan. Is there one, or have I already messed up? Because the derivative of tan is sec squared. Derivative of sec is sec tan. So I've already messed up. There's not one, is there? Because it'd be cosine over... Yeah, we'd have to do a u-do substitution. So we aren't going there. So let's change this problem so that it will be a little bit easier to work with here, okay? We don't want to jump another day ahead. We're going to redefine our function to be the integral from 0 to x of sec squared t dt. Okay? Now, so we're just going to forget about this that was written up here all nice and pretty. I'll have to change that later. Now what...
Create that?
I did. Now what function has a derivative of sec squared? Tan. Okay. So this means, this is just another way of saying that it is the tangent of x evaluated at 0, or excuse me, tan of t evaluated at 0 and at x. Well, that really we could really just redefine that to be f of x is the tangent of x minus the tangent of 0, right? Because if I put x in place of t, I'm going to get tan x out. If I put 0 in place of t, I'm going to get tan 0. And what's the tangent of 0? Anybody know? Tan is sine over cosine, so it'll be 0. Very good. So really, this function is just the tan x. Would you agree with that? Now let's see what we did. We took a funny looking function here that had an integral sign in it, so we integrated. And once we integrated, we evaluated at the two limits. The top limit had a new variable in it, x. And now how would you find the function value at 0?
You just plug and chug.
You just plug 0 in and chug it out.
0.
Now, understand what we just did. We just did this with the x there. So now it's nice and easy. We could have put the 0 there. We could have replaced the x right there with 0 and integrated from 0 to 0 of sec squared and went through all of the integration and figured out what it was. And then gone back and replaced the x with pi over 6 and figured out what it was. And gone back and integrated again with pi over 4 and pi over 3 and pi over 2. We could have integrated 1, 2, 3, 4, 5, 6 times. But if we integrate with the variable in here, now we just have to plug and chug. A lot easier that way, right? Now, let's think about what this would look like graphically. Is there anyone in the room that recalls what the secant function would look like if we were to graph it?
Wait, isn't secant just
Sec
like,
squared, I'm sorry.
No, I know what cosine and sine and tangent look like.
Yep. We know the sine has a nice little wave. The cosine starts at the top. The tan looks like S's.
Yeah.
Yep.
Lazy S's.
Yep. And then the secant turns one of them over, and secant squared, who knows what that does. So since we don't remember that, let's go back to our calculator here. And I don't really care that you do this. I just want you to watch it, okay? Y is secant. Well, I don't have a secant button, so it'll be 1 divided by cosine x squared. Okay? And what if we graph that so we get a picture of what that looks like? All right, you got some, it's not real pretty, is it? Where are we talking about? We're only talking about from 0 to pi over 2. So let's change our window on here. We're going to make our window from x is 0 until x is pi divided by 2. And then we'll graph it. Okay, so this is what our graph would look like. Now I'm going to try to tie several things together here with us, okay? This is a graph of sec squared. That was the original function that we had. When we integrate, what does that mean? What does that do? Finding the derivative of slope. Integrating is?
Finding the function.
We talked about it the other day. When I tell you to integrate, what does that mean that we're doing graphically?
Does it have to do with the area?
Very good. It's finding the area. Okay? So when we integrate sec squared, we're finding the area from one limit to the other limit, right? So remember when this function value up here had, or when x was 0, that would mean we were integrating from 0 to 0, right? Well, what would that look like down here? This is 0, and 0 is right back over the top of it. So what should the area be? 0. And lo and behold, that's what we would have gotten out. Now, what happens when we get to pi over 6, which would be right along in here? So we should get a number there. I want you to compare this area with, what about when we go all the way to pi over 4? Talk to me about the area from 0 to pi over 6 and the area from 0 to pi over 4. Pi over 4 is larger. Would you agree with that? What about when we go on to the next one, which was pi over 3? It's going to be even bigger. Kind of obvious here, isn't it, so far? And what about when we get to pi over 2? It's even bigger. When you see something like this, when you see something like this function here, this is going to be called, or is called, an accumulation function. What on earth does that mean? What happens if you accumulate things? You get more stuff. So this is an accumulation function. This function, it just simply continues to add area to itself because we're going from 0 to some variable up here. So an accumulation function is a function that simply adds to itself. So if you see something in an FRQ that says something about the accumulation function, you know you've got to have some type of integral from 0 to x, or from 1 to x, or from somewhere to x. That's the key thing I want you to walk away from right now with this, okay? Accumulation function is something that looks like this, has an integral from 0 to a variable, or 1 to a variable. A constant number down here to a variable. Are we clear with that? Not too complicated so far, is it? Okay? Good. Now, that's just something you need to keep in mind here. Now the second fundamental theorem of calculus. This is the big ticket. This is the headline for today, okay? If f, lowercase f, is continuous on an open interval containing a, misspelling, then for every x in the interval, this is true. Well, what does that say? Let's break it down. What does this right here tell us to do? Integrate. And what is this? The derivative. So what does this say? This says if we take a function and integrate it and then take the derivative,
it's a function.
It's what we started with.
Yes.
Doesn't that make sense?
Yes.
Yeah, I mean, it's kind of obvious there, isn't it? If we take a function, that's what we're saying here. That's what the second fundamental theorem of calculus says. If we take a function and we integrate it, and then we take the derivative of it, we get back to the original function. That's not, I mean, you can understand that. That's not too complicated at all to understand, is it? I want to rewrite it, though, with something that you need to be sure that because that's so easy you're never going to see it in a pressure situation. A more generic way of writing it would be this. d over du integral from a to u f of t dt is f of u times u prime. Okay? Now that's what you really need to be sure you remember. If we integrate something and then take the derivative, we should get back to the function. But what's different about u and just x here? Can anybody tell me? U is a function. Okay? U is a function. So what I'm saying is u could be x, in which case the derivative is what? 1. But what if u is x squared?
How do we know that u is a function?
Okay, that's what I'm saying as a definition here. This doesn't have to be just a nice long letter up there. Because remember, how did we start taking derivatives back 4 months ago? We'd say the derivative of cosine x or the derivative of tan x, and then it was easy. But then suddenly I threw the cosine of 2x in there, right? And then that got annoying because you had to remember your chain rule. We can still use the chain rule here. If whatever we're integrating to is something other than x, we just have to remember that it's the function at that value times the derivative of the function there. And we're fixing to talk about an example of that here in just a moment. Now, what is true of A? A is any constant number. Any constant number. Okay? So if we're integrating from 7 to x or 12 to x or 48 to x, as long as this number is a constant number, then it is okay. All right? It doesn't look like there's any math in that, does it? Okay, and there's not really. It's just you got to think of it up here. Okay, so not too complicated. There's second fundamental theorem of calculus. Let's blow through a few other things here. Real simple problem. What's the answer? The derivative of the integral from 0 to x of the square root of 3t squared minus 5t plus 6.
3t squared minus 5t plus 6.
Almost.
The root of.
Almost.
Wait, the derivative of the integral.
Uh-huh.
So it's just going to be something.
With respect to x, that's t.
3x squared minus 5x plus 6.
That's the answer.
That's the answer.
Is this going to be a real problem?
Could be.
Well, just fooled Sam and
I
Colin.
don't understand. Why you change it from t to x?
Okay. Think of this in light of the accumulation function that we dealt with earlier. With the accumulation function, we're going to a variable number up here. So we're changing variables in midstream. Midstream. We're changing the variable from t to midstream. There's a jackknife rig down the road here.
Oh.
Yeah.
Wait, what? On which end?
78 in Dalles Mill. A tractor trailer turn. Instead of being straight, the front end is turned that way, so there's a wreck down here. Okay. Okay. That's not hard, is it? If you don't believe it, you could integrate that mess. No, you couldn't. Not that one. But a simple one, you could integrate it, then take the derivative, go the long way around, and get there. But something like that, because we're never going to learn how to integrate square roots with stuff underneath them like that. Well, yeah, we are. But anyway, integrate and take the derivative, you have to get back to this. What changed from the original problem? The t's changed to x's. That's the only thing that changed. Everything else.
So should it be d plus 6 dx?
No, the dt is not underneath the radical here. Yep. We just integrate, take the derivative, we get to the same thing. All right, stop beating that horse. What changes here now?
It's the t again.
Mm-hmm. So it's going to be?
Your thing is cubed.
Right. So this is like the more generic formula I gave you. If we're going to find the derivative of this, f prime is going to be what? If we integrate this and then take the derivative.
It would be sine x, all that together.
Sine of that number, the sine of x cubed, times the derivative of x cubed, 3x squared.
So, chain rule.
Yes, so you're using the chain rule there. Now, I don't want you to do this, but I'm going to walk through that just the long way, okay? What function has sine as a derivative? All right, so it would be negative cosine evaluated at pi over 2 and x cubed. All right, so that would give me negative cosine x cubed minus negative cosine pi over 2. Right? That's just integrating it. Well, but that's not what my problem asked me to do, did it? It said find the derivative. So now that we've figured out that f of x is negative cosine x cubed plus cosine pi over 2. Well, what's the derivative of this? Now we need to find f prime. The derivative of cosine is negative sine, but we already had a negative, so it'll be positive sine of the argument times the derivative of the argument. What about the derivative of cosine pi over 2?
Negative sine pi over 2.
Everybody whiffed that one.
What was the question?
What's the derivative of cosine pi over 2?
Oh, it's 0.
It's 0. What is this?
Oh, it's a number.
That's a number. I didn't write it like a number to confuse you, and it worked. That's a number. The derivative of a number is 0. So this, let's highlight these differently. How can I change that color? All right. The blue was done the long way. I integrated it, and then I took the derivative of it. The red down here is just using the second fundamental theorem of calculus. If we integrate this and then take the derivative, it's going to be the sine of x cubed, the function evaluated at that, times the derivative of that x cubed up there. Let's look at another one right quick. Same piece of paper. If we've got f, capital F of x is the integral from 0 to ln of x of the ln of x dx. What is f prime of x? What is f prime of x?
Wouldn't it just be LX? Would it be LT?
Second fundamental theorem of calculus says it is this function, ln, evaluated at this number, ln of x, times the derivative of this up here, 1 over x. Did that get any clearer there? Okay, we're going to do one more because y'all haven't convinced me it's clear yet. I think you're telling me untruths. From 1 to cos x of x squared plus x. I like my x's. T squared plus t dt. What is g prime of x?
It would be plus cosine of x.
Times the derivative of what? Times the derivative of just this thing up here. What's the derivative of cosine? Minus sine x. I'm going to have to slide all this back so I can get it on here. Times negative sine x. Okay? That's all the second fundamental theorem of calculus says. All right? Not anything that's super hard there. I do want to look at a few problems that I think are actually going to help you with some of the questions that you've got from me right now. So we're going to keep looking at these next few problems here. A chemical flows into a storage tank at a rate of 80 plus 3t liters per minute, where t is between 0 and 60. Find the amount of chemical that flows into the tank during the first 20 minutes. Okay, can you picture what we've got here? We've got a tank. It's got nothing in it. Somebody cuts on the spigot up above it, and chemical starts pouring in at this rate right here. Find the amount of the chemical that's in there after 20 minutes. What on earth do we do with that? Integrated. Why do you think integrated? Okay. What is this 80 plus 3t? It's a speed. It's a rate at which something's coming in. So if we want to, this is dc dt is 180 plus 3t.
What's C for?
The chemical.
Oh.
I just made that up because I didn't know. Now, what are we asked to find? Find the amount of chemical. That's not a rate. It's not a derivative of rate. It's saying how much of it. So in order to do that, we need to integrate 180 plus 3t. Now, do you think that this question requires a real number answer? Well, then I've got to have limits of integration. 0 to 60? 20? Which one?
The limits are 0 to 60.
Okay. Why?
Because, I think the
Can everybody agree on 0?
0 is yes.
Okay.
0.
Find the amount of chemical that flows into the tank during the first 20 minutes. So we're wanting to know how much, not how much came in over the entire time the spigot's on, how much came in the first 20 minutes. Okay? So integrate 0 to 20. That's not a hard problem now, is it?
Oh, no.
Because you've been doing, you haven't done that homework yet. But if you had done that homework, this would be just like the homework that you haven't done yet. Okay? So, I'm going to leave that. Now let's go ahead and solve that out and get a real life number. We'll feel better then. 180t plus 3t squared over 2 evaluated at 0 and 180. Not 180, 20, right? So I got 180 times 2, 20, plus 3 times 20 squared over 2. 3,600 plus
600.
600, okay. $4,200 liters. So after 20 minutes, if everything stays like it says in that problem, there's 4,200 liters of that chemical in the tank. Okay? Not too complicated yet, is it? Ready to move forward? Okay. Big ticket here. Big ticket here. When calculating the total distance traveled, okay? I want you to watch me right now, okay? I'm going to take 2 steps over here. I'm going to take 1 step back. How far have I traveled? 3 steps. Because I went from here to here, 1, 2, then I turned around and took another. I took 3 steps. That's how far I traveled. How far am I from where I started? 1. Okay? So see, Colin could have stood up here and taken 3 steps and be at a totally different place than I was. Agreed? But we both traveled the same distance. Displacement is different, okay? Displacement talks about where am I in relation to where I started. Okay? And look at what that is. That's just integrating from one end to the other.
Oh, then this is traveled.
Okay? So if I was talking about this, if I had done that in 3 seconds, let's say, okay? I was standing here. In 2 seconds, I was here. At the 3rd second, I was here. If we integrated that function, whatever it might look like, from 0 to 3, we would get this number right here, where I'm at right now. Distance traveled is how much movement I did. That would need to be the 3 in the example I just talked through. And notice what we integrate to get it. We don't integrate the velocity, we integrate the what? Can anybody see that on your screen or my screen? We integrate the absolute value of the velocity. Okay? Now, you can integrate the absolute value, or you can just find out where did the velocity become 0. Okay? So this is doing this, or like if you know that the velocity turned 0 right there at that point, call it C. And the velocity turned 0 right there at that point, call it D. You can integrate from A to B. You'd integrate from A to C, plus integrate from C to D, plus integrate from D to B. Okay? So you've got 2 options here. You can integrate the absolute value, or you can find the zeros of the velocity and integrate from one end to the 0, from the next end to the 0, from the next end to the 0, and make all your answers positive. Tell me something about when I integrate, if this is my function that we're looking at up here, if I integrate from C to D, tell me something about that answer. It's going to be negative. So when you integrate that, just know in your mind, make it positive. If I'm trying to find distance. Because this says a displacement. I've moved back towards where I was to begin with. Or I moved in a negative direction from what I was moving. But I still moved. You know, if I was here and I took 1 step backwards, my velocity was negative, but I was still going at a speed of 1. You're with me there? I just still travel the same distance. The distance is still a positive number. So, two things to do here. One, integrate the velocity, the absolute value of the velocity. Or two, find the zeros, integrate from one zero to the next, and make everything positive. Those are your two options. I hope you heard that. Okay? That will really help you on some of the FRQs that you're going to have over the next 10 weeks. Yep. All right? Any questions about that? That's a big ticket there. All right, let's look at this problem now and see if we can use what we just talked about. A particle is moving along a line so that its velocity is this. What is the displacement of the particle on the time interval 1 to 5? What does that mean? All right, so tell me what I'm going to do. Displacement of the particle. So I integrate what? I just integrate the velocity from where to where?
From
1 to 5. Okay?
But you have to...
Do I need absolute value in A part?
No.
Because?
It's displacement.
It's displacement. Okay? Now, if any of you have one of these lovely devices, wouldn't it be nice if this would do that problem for you? Really would, wouldn't it? Well, let's see if we can figure out how to make it do that. All right? I am going to go to my y equals, and I am going to type in that function, okay? So I'm going to type that function in. X raised to, I need to put it right there so I can get x raised to the third minus 10. I hate when this calculator does that for me. X raised to the third minus 10 x squared plus 29x minus 20. Okay? So there's my function. I'm wanting to integrate that from 1 to 5. So I need to be sure that 1 and 5 are both in my window, okay? So I'm just going to go to my window, which is the next button over, and be sure that my x-min and x-max is between 1 and has 1 and 5 in it. So I'm going to go from 0 to 10. I could really go from 0.5 to 5.5 or 0.75, but anything so that the two of them are in there, okay? Now, if I go to, I think it's math. Is it math? No, I'm sorry. It's second trace. Look at number 7 down there. What does that look like? What does number 7 look like down there in the calculator?
The integration of a function of a derivative.
Okay, so we're going to say 7.
Whoa.
I want to integrate that function. Second trace under calc. My lower limit, where do I want to start integrating? 1. Where do I want to stop integrating? 5. And it draws you a pretty little picture.
10 and 2/3.
10 and 2/3. That's what that answer is.
So is that acceptable to me?
That is acceptable when you are allowed to use your calculating device, which is not very often.
Are we allowed to use our calculating device on our test for this class?
I don't know about the next one, if you are or not. If you could, then yes, it'd be fine for you to do that. But you've got to understand, my answer to this is kind of like the open book test. How often do you say, oh, please give us an open book test to teachers? Have you heard my answer to that? If I'm going to let you use your book, you don't want to take the test. Okay? You just don't want to. So if I can tell you you can use your calculator, yeah, you might be able to do this on one of them, but I'm not testing whether or not you can punch your buttons.
But I can punch the buttons so well.
You're 18 years old, you're in AP Calculus. If you couldn't punch the buttons, you wouldn't be here, okay?
So good at the buttons.
So, but here's the reason I'm showing you this, okay? A part, boom. Now, what's B part asking for? Is it asking for the same thing?
No.
It's not?
Distance.
Distance. So how does that change our problem? We're still going to integrate. We're still going to integrate 1 to 5. But what does it change? We're now integrating the absolute value of that function, aren't we? And absolute values are a boogabeer to integrate. If you're going to do that, you're going to have to find the zeros and break up into it. And that's not any fun at all by hand. But with your calculating device, if you go to y equals, and in front of our function, we can insert a math function, I think. Where's that math function at?
I've seen it before.
Yep. Math num1, ABS.
And then close the parenthesis.
Mine's not going to do it that way. But see, mine puts my absolute value bars there. If I can move my function inside my absolute value bars, which I can't, but I'm going to try. I'm going to put it there. So I want to do math num absolute value bars. Now my function is x raised to the third minus 10x squared plus 29x minus 10, no, minus 20. And now I've got my function in there. Now if I integrate, first of all, look at the graph. Does anybody know how that graph looks different than the other one? Does anybody remember what the other graph looked like? That little piece right there. What did it do to it? It flipped it over to make it an absolute, because absolute value means it's positive. So it took everything that was below the absolute value right in here and turned it upside down. But we still want to integrate from 1 to 5. And look what we got this time. 11.833333. And I promise you that's far easier than you integrating this sapsucker by hand. Far easier. What you got?
It says invalid something. Like I'll press 7. Invalid.
Invalid dimensions. Well, let's see. See if we can figure that out. I don't know. Can we just graph? It won't graph either. So it's not liking something. Oh, I bet it's not liking something about your. Oh, you've got plots on. There we go. We cut plots off. Now it'll graph. Now it'll work. Plot was off.
I've got random little squares on mine that I don't remember.
Okay, we'll look at that in just a second. Any questions?
I mean, it does the math correctly. It's just squares.
Any questions? I know you're about to sleep, so I'm going to stop lecturing, okay, and let you have fun with whatever you need here.